Usually when we talk about the electric vehicle revolution, there is this underlying expectation of total limitlessness, right? We are conditioned by our smartphones and our laptops.
Right, totally. You just buy the shiny new device, you find a plug, you get your juice, and you go.
Exactly. It's supposed to be clean, simple, and infinite, like a totally seamless leap into the future for you, the driver. Yeah, you pull up to a sleek, glowing charging pedestal, you plug in your vehicle, and the power is it's just waiting for you on demand, no matter where you are.
But then, you look behind the curtain. You look past the shiny plastic of those charging pedestals, and you realize that this limitless plug is actually fundamentally broken.
It really is. We are looking at a technological landscape that is accelerating at breakneck speed, only to crash face first into a massive, invisible wall.
And that wall is the global electrical grid. Welcome to today's deep dive, where we are going to look right at that invisible wall. It's the absolute definition of a critical infrastructure bottleneck. I mean, we're essentially trying to push 21st century hyper-advanced vehicle technology through 20th century copper wiring. And, well, the physics simply do not add up.
Right, which is why today we're on a mission to uncover the hidden mechanics and the incredibly clever business models keeping this whole revolution from just, stalling out. Because the reality is the local power plant simply cannot keep up with the cars rolling off the assembly line.
It really can't.
To do this, we are pulling from a massive stack of sources today. We've got a global market forecast on the business of charging from Fortune Business Insights. We have a really detailed blog post by energy practitioner Camille Talar, a news release on the City of Dallas municipal fleet, and some crazy specs from Udenko.
Yeah, and we'll even look at the UK pricing and specs for the ultra-luxury Denso D9 MPV.
So we've got a lot of ground to cover. But what stands out across all these different viewpoints, from the micro-level engineering of a single parking lot to billions of dollars in global market shifts, is a fundamental change in strategy.
Right, because the solution to our grid problem is not necessarily tearing up the streets to lay more wires. The solution is smarter storage.
Smarter storage. I love that framing. But before we get to the massive batteries and the mobile powerhouse units, we really have to understand why plugging a fast charger into the grid is currently such a nightmare.
It's a massive headache for developers right now.
Yeah, and one of our technical sources, the Camille Talar piece, drops a statistic that honestly made me do a double take. Industry reporting finds that 50 to 80% of candidate EV charging sites face constrained or insufficient grid connections.
Wait, 50 to 80%. Think about the gravity of that for a second. Over half of the locations where a developer actually wants to put a fast charger, where the highway traffic studies are solid, the land lease is already signed, and the customers are literally driving past, they can't even turn the site on.
Right. The chargers themselves are not the bottleneck at all.
No, it's the physical copper buried in the ground. It just cannot move the 2 or 3 megawatts of power required to run the station.
And it is not like, calling your internet provider to bump up your bandwidth. Upgrading a commercial grid connection is a grueling process.
Oh, absolutely. You are looking at new transformers, massive substation upgrades, heavy civil engineering.
And the data shows this takes anywhere from 12 to 36 months, 2 to 3 years.
Yeah, and it costs between 150,000 and 3 million euros. That is a paralyzing hurdle for any business trying to open a station.
It's insane. Why is it so hard, though?
Well, it fundamentally comes down to the nature of how we have historically consumed electricity versus how the grid was engineered to deliver it. A standard commercial grid connection is built to deliver power in a thin, steady trickle.
Like baseline stuff, right?
Exactly. It is designed for baseline loads, running the lights in a supermarket, keeping refrigerators cold, powering office computers. And a modern fast charger demands a massive, violent burst of power the little second a car plugs in.
Okay, let's unpack the mechanics of this, because I want to make sure you, the listener, are visualizing this correctly. It is like trying to fill a massive 10,000-gallon fire engine using a tiny garden hose.
That's a great way to look at it.
Right. You just cannot get the volume of water you need in the 15 minutes you have. But instead of paying 3 million euros to tear up the street and lay a massive industrial water pipe, we just put a giant water tower in the middle of the parking lot.
Yes.
We let the tiny garden hose slowly fill the water tower all night long, and when the fire engine arrives, we just open the floodgates and dump the whole tower into it once.
That is the perfect mechanism to understand what the industry calls a behind-the-meter battery energy storage system, or ESS.
Behind the meter. Okay.
Yeah, so the grid trickles energy into the battery continuously, 24 hours a day, keeping the demand totally flat.
Okay.
Then, when a burst of hungry vehicles arrives, the utility connection just continues its quiet little trickle, but the massive battery discharges hard into the chargers.
So the local substation never even feels the spike.
Exactly. The grid never gets overwhelmed, and the cars get their ultra-fast charge.
Now, diving into the chemistry of that water tower, the research specifically highlights the use of LFP, or lithium iron phosphate batteries, for these storage systems. Why that specific chemistry? Like, why not just use the batteries we put in the cars?
It all comes down to thermal stability and cycle life. The crystalline structure of iron phosphate is incredibly robust. A charging buffer battery works so much harder than a car battery.
Because it's constantly working.
Right, it cycles aggressively. It's sometimes taking on energy and discharging it simultaneously multiple times a day with these incredibly sharp output bursts. An LFP pack can easily handle 3,000 to 6,000 full cycles with minimal degradation.
Oh, wow. And a standard car battery couldn't do that.
Well, older chemistries, or the nickel manganese cobalt batteries you often find in cars to save weight, they might only manage 1,000 to 2,000 cycles under that kind of industrial stress before they really start breaking down.
But wait, LFP batteries are heavier, right?
They are, but for a stationary water tower, weight does not matter. They are basically the indestructible heavy lifters of the energy world.
Okay, but I am doing the math in my head here, and I have to push back a little bit. A massive industrial-scale LFP battery system cannot be cheap. We are talking millions of dollars for the battery, the inverters, and the climate control systems, right?
Yes, it's a significant upfront cost.
So if developers are dodging a €3 million grid upgrade just to buy a €2 million battery, the math still feels a little broken to me. Plus, eventually, even an LFP battery dies. So isn't laying thicker copper ultimately more permanent? Like, you endure the construction, you lay the wire, and it is done for a century.
What's fascinating here is that that is the traditional way of thinking, right? But if we connect this to the bigger financial picture, we have to recognize the difference between a sunk cost and a performing asset.
Okay, how so?
Well, this requires us to understand power versus energy from the technical briefings. Power, measured in kilowatts, is how hard the electrical system can push instantly. Energy, in kilowatt hours, is the total volume it can hold.
Right.
When you pay a utility 3 million euros to dig up a highway and lay thicker copper, you are only buying power capability. That copper is a sunk cost. It will never generate a single dime of revenue on its own.
Because it just sits there waiting for a car to plug in.
Precisely. But a battery provides optionality.
Yeah.
First off, you can commission a battery in 3 months instead of waiting 3 years for the utility company to clear permitting.
Which is huge for a business timeline.
Exactly. Second, if you build a charging site and the traffic patterns change, like maybe a new highway bypass is built and your station becomes a ghost town, you can literally unbolt the battery, put it on a flatbed, and move it to a busier location. Try doing that with underground copper.
Yeah, that copper is staying in the ground forever.
And perhaps most importantly, the battery can actively trade energy. It buys cheap off-peak power at 2 in the morning and dispenses it, or even sells it back to the grid when prices spike at 6 in the evening. It is an asset that pays for itself.
Okay, that makes a lot of sense. So the battery isn't just a Band-Aid for a weak grid. It is a highly calculated financial instrument.
Exactly.
But what if you are in a situation where you don't even have that garden hose trickle of power? What if you were looking at a site where grid upgrades aren't just 3 years away, they are completely impossible?
Well, this brings us to a really fascinating pivot in the industry, bypassing the grid entirely. We move from buffering a weak grid to going completely off-grid.
And this is exactly what the city of Dallas is doing with their municipal fleet. The news releases show they just placed their 4th order for these units called Beam Global EV ARC systems.
Right, the Beam Global systems.
And what blew my mind looking at the specs is that these things are entirely solar powered, and they require absolutely zero construction, zero trenching, and zero electrical permitting. You literally just drop them into a parking space.
And that zero permitting detail is the secret weapon here. Electrical permitting for high-voltage infrastructure requires environmental reviews, zoning board approvals, utility load studies. It is a bureaucratic nightmare.
So they just skip all of that.
By dropping in a self-contained solar generator and battery, Dallas completely circumvents the 36-month timeline. These ARC systems generate and store their own renewable electricity. They operate entirely independently of the Texas utility grid.
Which is huge for Texas, honestly, given their grid history.
Tremendous. Dallas has been stockpiling these units because they provide instant operational resilience. If a massive storm takes down the main grid or there are rolling blackouts, the municipal fleet, like the code enforcement vehicles and local utility trucks, they can still charge up and respond to emergencies.
Right, the grid's failure does not become the city's failure.
Exactly.
But those solar units are meant for slower, overnight fleet charging. If we want to talk about raw, drop-in, hyper-fast power, we have to look at the Udenco DC mobile powerhouse charger. I was reading the engineering sheet for this machine, and it is an absolute beast.
Udenco has engineered what is essentially a quantum leap in portable, high-density energy.
Just listen to these numbers. It provides 400 kilowatts of charging power from a 350 kilowatt-hour liquid-cooled battery.
That's a massive amount of power.
Yeah, and it weighs just under 7,000 kilograms, which is about the weight of a full-grown African elephant, just packed entirely with high-density cells. It features 2 high-power connectors and an IP65 environmental rating.
Let's translate that IP65 rating for a second because it really speaks to how this machine is used. IP65 means the unit is totally dust-tight and protected against powerful jets of water from literally any direction.
So it's basically weatherproof.
More than weatherproof. You can drop this 7,000 kilogram power bank into a muddy disaster relief zone, a gritty industrial mining site, or a remote highway construction project in the pouring rain, and it just works.
And we should probably highlight the liquid cooling aspect too, right?
Yeah.
Because pushing 400 kilowatts of power isn't like charging your laptop.
Not at all. Pushing 400 kilowatts generates an immense, dangerous amount of thermal energy. Air cooling simply cannot dissipate the heat fast enough when you are dealing with that level of amperage.
Right, it would just overheat immediately.
Yeah, if the cables and the battery cells aren't actively chilled by liquid coolant running through these microchannels, the system would literally melt itself.
Which makes the next spec even more impressive. Despite all that power and liquid cooling, it operates at 55 decibels. That is ultra quiet. We are talking about the volume of a household refrigerator.
And that acoustic design is super intentional. If you are managing a disaster zone, or you've dropped this unit into a quiet residential neighborhood to support a temporary construction fleet, the last thing you want is the deafening roar of a massive diesel generator.
Right, nobody wants to hear that.
Exactly. The modularity here changes the entire calculus of infrastructure. You don't have to bet millions of dollars on unpredictable grid forecasts anymore. You just drop in an off-grid powerhouse. If the EV demand materializes at that location, great, you leave it there. If the demand moves, you load the elephant onto a truck and follow the market.
Okay, so the engineering is brilliant. We can buffer weak grids with massive LFP water towers, and we can bypass the grid entirely with these mobile drop-in behemoths. But let's get back to the money for a second.
Always back to the money.
Always. A 350 kilowatt-hour liquid-cooled battery or a massive stationary BES takes serious capital. Who is actually fronting the cash for all this hardware?
That leads us straight into the financial engine making this entire hidden ecosystem possible. Charging as a service or CUS?
KRS. The market forecasts on this from Fortune Business Insights are staggering. Analysts project the KRS market to explode from roughly $16.8 billion in 2025 to over $130 billion by 2034.
That is massive growth.
It really is. That is a compound annual growth rate of nearly 25%. The Asia-Pacific region is currently dominating this space, but the research shows that commercial applications are driving this explosive growth globally. Logistics vans, ride-hailing services, public transport networks, they are all rapidly electrifying.
And the reason a 25% growth rate is sustainable is because KRS solves a fundamental business problem. It removes the upfront capital expenditure.
Right.
If you own a fleet of delivery vans, your core competency is logistics. You are in the business of delivering packages on time. You do not want to become a high-voltage electrical engineer, and you certainly don't want to tie up millions of dollars of your operating capital building mini power plants in your parking lots.
So the KRS provider basically takes on all that friction.
Exactly. The provider comes in, deals with the utility, installs the fast chargers, drops in the battery buffers, layers on the energy management software, and maintains all the hardware. You, as a fleet owner, just pay a predictable usage-based fee, like Tesla's pay-per-car wash, or a fixed monthly subscription, like Ionity's model.
So if you are listening to this and you are just a regular person driving an EV, Does Kai-once mean you are staring down the barrel of yet another monthly subscription in your life? Like paying for streaming services, but now it is for your daily commute.
I completely understand why that model sounds alarming to the everyday driver. But the reality is that the Kiot model, and specifically those massive battery buffers, is actually protecting you from a hidden killer in EV economics. It is a utility billing mechanism called demand charges.
Demand charges.
Yeah.
I have to admit, this was a completely new concept to me when digging through the energy practitioner notes.
It is the quiet killer of charging site economics. You see, a utility company doesn't just bill a commercial site for the total volume of energy they consume over the month. They also bill them a demand charge based on the absolute highest spike in power usage they hit, usually measured in a rolling 15-minute window.
Right, why do they do that?
Because the utility has to build physical power plants and transmission lines capable of supporting your absolute worst-case scenario. Even if you only pull 2 megawatts of power for 15 minutes all month, the utility has to maintain 2 megawatts of infrastructure capacity just for you, 247.
Oh, wow.
So they penalize you for the spike. Imagine a quiet highway charging station on a Tuesday. Suddenly, 3 fast-charging vehicles pull up at exactly the same time. They plug in, demand massive power for 15 minutes, and then drive away. The station might use barely any electricity for the rest of the week.
But returning to our water tower analogy, if the local water company billed you for the entire month based on the single fastest rush of water you used when you flushed every toilet in the building at exactly the same time, you would go bankrupt.
That is the perfect way to look at it. That single 15-minute spike can cost a site thousands of euros or dollars a month in utility penalties, instantly ruining the site's profitability. Grid costs can run 40 to 60% of an operator's total monthly expense purely because of these demand charges.
And this is where the battery buffer steps in to save the day, right?
Yes. The battery uses that slow, cheap trickle from the grid all day, keeping the grid draw perfectly flat. When those 3 cars pull up, the battery dumps its stored power into the vehicles.
Ah.
The utility meter on the street only ever sees a smooth, low-level import of electricity. The battery literally erases the peak, completely dodging the catastrophic demand charge.
So by saving the operator thousands of dollars in utility penalties, the battery is what keeps the cost of a kilowatt hour low enough for the consumer to actually afford. It is entirely invisible to you when you swipe your credit card, but it is the financial linchpin of the whole operation.
Without that battery buffering the demand charge, the cost to charge your car on the highway would easily double or triple.
Well, the systems we just discussed are about to be pushed to their absolute limits. Because the vehicles arriving on the market right now, the next generation of EVs, are hungrier for power than anything we have seen before. Consider what happens when the new ultra-luxury hyper-EVs hit the streets. Take the new dependency D9, for example.
Ah, yes, the ultimate stress test for the grid.
The Automotive Reports just announced the UK pricing for this vehicle. It is an ultra-luxury 7-seat MPV starting at £75,000 for the elegance trim and up to £85,000 for the ultimate.
Not cheap.
No, definitely not. It features a DMI AWD plug-in hybrid powertrain with a massive battery, giving it 130 miles of electric-only range and 590 miles combined. But the staggering statistic is how fast this vehicle drinks electricity. The D9 utilizes something called slash charging. It can take that battery from 10% to 70% in just 5 minutes.
5 minutes. If you calculate the energy transfer required to do that, you are looking at an equivalent maximum charging power of 559 kilowatts for a single passenger vehicle.
Here is where the math gets genuinely terrifying for a grid operator.
Yeah.
Say you build a luxury charging hub outside of London, and 6 of these dependency D9s pull up at exactly the same time. 6 vehicles multiplied by 559 kilowatts. You would need a massive 3.3 megawatt grid connection just for a handful of minivans.
It's mind-boggling.
And that is before we even look at the commercial sector. The specs for megawatt charging systems, or MCS, designed for heavy electric transport trucks, are pushing 1 to 3.75 megawatts of power for a single truck. At that point, a single truck charger outdraws an entire logistics warehouse.
This raises a very critical friction point, though. How does the local grid not instantly melt down when 6 D9s or a couple of heavy haulers plug in simultaneously? This is where we have to introduce a physical reality of battery chemistry that the energy engineers call the simultaneity factor.
Okay, wait, so my naive math of multiplying 6 by 559 is actually wrong.
Exactly. The naive math assumes every car is pulling maximum power from 0 to 100% of the charge. But in reality, due to internal resistance in lithium-ion cells, vehicles do not charge at maximum speed the whole time.
Why not?
Well, as a battery fills up, it becomes harder to push electrons into it. It's called the charging curve. If you keep forcing 500 kilowatts into a battery that is already at 80% capacity, the internal resistance will generate so much heat the battery will literally catch fire.
Oh, yikes.
So the car's internal software tells the charger to throttle down. A car might pull that massive spike at 20% charge, but drop down to 80 kilowatts by the time it reaches 70%.
So an ultra-fast charger capable of 350 kilowatts might only average, what, 130 to 170 kilowatts over the duration of the entire session.
Which means even if all 6 Dense D9s are plugged in, they are not all demanding that massive spike at the same millisecond. Some are just starting and pulling hard, others are tapering off. The genuine peak demand of the site is usually only 50 to 70% of what the naive math suggests.
But you still can't just cross your fingers and hope all 6 drivers don't arrive with empty batteries at the exact same moment. You need a system to manage it, right?
And that requires incredibly sophisticated real-time energy management systems like the Disperon platform highlighted in the technical briefings.
Think of the software like an air traffic controller at a major airport during a thunderstorm.
That is a brilliant way to conceptualize it.
The air traffic controller, the Disperon software, is looking at the sky. It sees a massive electric semi-truck coming in that desperately needs a megawatt of power right now. That is an emergency landing. But it also sees a passenger car that is already at 80% charge, just trickling along. The software instantly recalculates. It puts the passenger car in a holding pattern, slightly throttling down its power feed, and diverts the heavy flow from the battery water tower directly to the truck.
All while enforcing a strict hard cap on the grid import so the utility connection is never exceeded. It is balancing grid import, battery discharge, and the unique taper curves of half a dozen different vehicles hundreds of times a second.
So it's constantly doing the math.
Yes, the battery never gets overwhelmed, the demand charge is never triggered, and every vehicle gets the fastest possible charge their specific chemistry can handle at that exact moment.
It is a phenomenal high-wire act of software and heavy engineering. We started this deep dive with a very real fear of grid failure, the invisible wall that was supposed to stop the EV revolution in its tracks. And instead of a crisis, we uncovered this thriving, hidden ecosystem.
We really did.
We have got indestructible LFP battery water towers buffering the grid, off-grid solar tech like Beam Global, circumventing years of permitting, drop-in liquid-cooled mobile powerhouses from Udenko, and clever chaos business models slaying utility demand charges to make the economics actually work.
So the next time you pull up to a hyper-fast charger on the highway and you get that magical 5-minute top-up, I want you to remember what is happening behind the plastic pedestal. You aren't just plugging a cord into the local power plant. You are interacting with a highly orchestrated, intelligent, local microgrid. It is a system that has been quietly banking energy all night, managing thermal loads, and doing complex calculus just for your arrival.
Which brings me to one final, mind-expanding idea, pulled right from the margins of a Camille Tallar blog post. We've spent this entire deep dive talking about huge stationary batteries buffering the grid to feed the cars. But what happens in a few years when millions of EVs sitting idle in driveways and office parking lots reverse the flow?
Oh, this is the really wild part.
The engineering term for this is vehicle-to-grid, or V2G. Could the cars themselves, with all those massive liquid-cooled batteries, become the very buffers that finally upgrade our global grid? Imagine plugging your car in, not to take power, but to serve as the water tower for your entire neighborhood during a peak demand spike.
It completely flips the script. The infrastructure bottleneck suddenly becomes the ultimate distributed solution.
That limitless plug might not be broken after all. It just needed to learn how to flow in both directions. Thank you for joining us on this deep dive. Keep questioning the hidden systems that power your world, and we will catch you next time.